Consider ethine CH triple bond CH. The structural formula of ethine is given. From the structural formula, it is clear that each carbon has to form 2 sigma bonds and 2 pi bonds. The triple bond is made up of 1 sigma and 2 pi bonds. So let us now try to find out the state of hybridization of both the carbon atoms present in ethine. The atomic number of carbon is 6, so the electronic configuration can be written as 1s2, 2s2, 2p2. So in the ground state, there will be 2 electrons in the 2s orbital and 2 electrons in the 2p orbital. In the excited state, 1 electron from 2s orbital will be promoted to the vacant 2p orbital. The total number of sigma bonds to be formed by carbon is 2. Therefore, we can say that there should be 2 hybrid orbitals available with both the carbon atoms. So here, one 2s orbital will mix with one 2p orbital to give 2 sp hybrid orbitals, and that leaves behind 2 unhybridized p orbitals which will be used in forming pi bonds. So each carbon atom in ethine is under sp hybridized state and 2 hybrid orbitals are available. Now let us see how the carbon-carbon sigma bond is formed. It is formed by the overlap of the sp hybrid orbital of one carbon with the sp hybrid orbital of the other carbon atom. And the CH sigma bond is formed by the overlap of the sp hybrid orbital of carbon with the s orbital of hydrogen. The 2 pi bonds are formed by the sideways overlap of the p orbitals available with both the carbon atoms. That is, the px orbital of one carbon atom will overlap with the px orbital of the other carbon atom to form a pi bond, and the py orbital of one carbon will overlap with the py orbital of the other carbon atom to form the second pi bond. So that is how the 2 pi bonds are formed. Consider PCl5 phosphorus pentachloride. Phosphorus atomic number 15 and the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p3. Therefore, in the ground state, there are 2 electrons in the 3s orbital, 3 electrons in 3p, and phosphorus will be having empty 3d orbitals. In the excited state, 1 electron from the 3s orbital will be promoted to the vacant 3d orbital. Now in PCl5, 5 sigma bonds are to be formed. So there should be 5 hybrid orbitals available with phosphorus, which is the hybridization that can give 5 hybrid orbitals. And how will it be formed? One 3s orbital will mix with 3 3p orbitals and 1 3d orbital to give 5 sp3d hybrid orbitals. So that is how the state of hybridization of phosphorus is taken as sp3d hybridization. 5 hybrid orbitals will be available with phosphorus. Now let us see how the PCl sigma bonds are formed. Each of the PCl sigma bond is formed by the overlap of the sp3d hybrid orbital of phosphorus with the pz orbital of chlorine. We have both axial chlorine atoms and equatorial chlorine atoms. Therefore, the bond angle will be 120 degree and 90 degree. The molecule is therefore trigonal bipyramidal. Consider the next molecule, sulphur hexafluoride Sf6. Atomic number of sulphur is 60 and the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p4. So in the ground state, there are 2 electrons in the 3s orbital and 4 electrons in the 3p. Empty 3d orbitals are available with sulphur. So in the excited state, 1 electron will be promoted from the 3s orbital to the vacant 3d orbital. Similarly, 1 electron from the 3p orbital will also be promoted to the vacant 3d orbital. In sulphur hexafluoride, 6 bonds are to be formed. So 6 hybrid orbitals should be available with sulphur. So which is the hybridization that can give 6 hybrid orbitals, and how will it be formed? Here One 3s orbital will mix with 3 3p orbitals and 2 3d orbitals to give 6 sp3d2 hybrid orbitals. So sulfur is under sp3d2 hybridized state. Now let us see how the Sf sigma bonds are formed. Each of the Sf sigma bond is formed by the overlap of the sp3d2 hybrid orbital of sulfur with the pz orbital of fluorine. Here the bond angle is 90 degree. Therefore the molecule is octahedral.